Hello everyone, my name is Saikia and I'm going to discuss the solutions to the problems given in Sessional Test 2. Information related to my profile is given here. So, about this presentation is made for the solutions to the given questions in Sessional Test 2. Our course instructor is Dr. Parag Manikarika. So coming to the questions. Question number 1. For a flow in the xy plane, the x component of velocity is given by u is equal to ax into y minus b, where a is equal to 1 feet inverse second inverse, b is equal to 6 feet, and x and y are measured in feet. Find a possible y component for steady incompressible flow. Is it also valid for unsteady incompressible flow? Why? How many y components are possible? Solution to question number 1. The given data, as you can see here, is shown. We have to find possible y component for steady incompressible flow. To also find if it is valid for unsteady incompressible flow. Why? How many y components are possible? Basic equation. Del x of rho into u plus del y of rho into v plus del z of rho into w plus del t of rho is equal to 0. We are assuming that the flow is incompressible and in the xy plane. Here del x of u plus del y of v is equal to 0. Del y of v is equal to minus del x of u. So the final result we get is equal to minus a into y minus b. This is obtained on differentiating u with respect to x, partial differentiating u with respect to x. That is del x of u as you can show, as it is shown here, ax into y minus b. So this is obtained. On integrating, we get minus a into y square by 2 minus b into y plus f of x. Here f of x can be taken as a constant. V of x comma y is equal to minus integration a into y minus b dy, as obtained in the previous page. Basic equation as given in the previous page is generally valid for unsteady and steady flow, as time factor or time dependency is unknown. Time is explicit as in the conditions given. Also, infinite solutions can be seen as f of x is unknown, and it can be anything, any function. So we are taking the simplest, f of x is equal to 0, and putting the values for a and b in the obtained equation for v x comma y. We get 6y minus y square by 2. This is the required solution. So coming to question number 2, we consider the velocity field capital V vector is equal to capital A into x to the power 4 minus 6 x square y square plus y to the power 4 I cap plus capital A into 4xy cube minus 4x cube y j cap in the xy plane, where capital A is equal to 0.25 per meter cube second inverse and the coordinates are measured in meters. Is this a possible incompressible flow field? Calculate the acceleration of a fluid particle at point xy is equal to 2, 1. Solution to question number 2. Given velocity field, we have to find is this a possible incompressible flow. Calculate the acceleration of a fluid particle at point x, y is equal to 2, 1. We know about the equation which can be used for incompressible flow. That is del x of capital U plus del y of capital V is equal to 0, and the equation capital A subscript small p is equal to capital D dt of capital V vector is equal to u into del x of capital V vector plus v into del y of capital V vector plus w into del z of capital V vector plus del d of capital V vector. Total acceleration is equal to converted to acceleration. First three terms of RHS, that is this term, and this term. This together make the converted acceleration, and the last term makes the local acceleration. Here u x, y is equal to capital A into x to the power 4 minus 6x square y square plus y to the power 4, and vx comma y is equal to capital A 4xy cube minus 4x cube y. From the given velocity field, this 2 can be taken. Using del x of u plus del y of v is equal to 0 as it is incompressible flow. So del x of capital A x to the power 4 minus 6x square y square plus y to the power 4 is equal to capital A into 4x cube minus 12x y square, and del y of capital A into 4x y cube minus 4x cube y is equal to minus capital A 4x cube minus 12x y square. So now acceleration, capital D dt of u is equal to u into del u del x plus v into del u del y plus v into del z of u plus del t of u, and acceleration in y direction is equal to capital D dt of v is equal to u into del x of v plus v into del y of v plus w into del z of v plus del t of v. So now acceleration in x direction is equal to capital A into x to the power 4 minus 6x square y square plus y to the power 4 del x of capital A x to the power 4 minus 6x square y square plus y to the power 4 plus capital A 4x y cube minus 4x cube y del y of capital A into x to the power 4 minus 6x square y square plus y to the power 4. This particular equation is taken as equation number 1. Equation number 1 gives ax is equal to 4 into capital A square into x square plus y square raised to the power 3. This is obtained on further simplification of the equation obtained for acceleration in x direction, and similarly for acceleration in y direction, the values can be put and the solution can be obtained on further simplification of this particular equation. In both the equations, w into del z of u is equal to 0 and del t of u is equal to 0. So hence at 2, 1, ax is equal to 62.5 meter per second square, which is obtained on further calculating by putting the values, and on further simplification this particular value is obtained for acceleration in x direction, and 31.3 meter per second square acceleration in y direction. This can be obtained on putting of the values and on further simplification. So acceleration is equal to 69.9 meter per second square is the resultant acceleration which can be obtained on using this particular formula. So coming to the question number 3, an incompressible liquid with negligible viscosity flows steadily through a horizontal pipe. The pipe diameter linearly varies from 4 inch to 1 inch over a length of 6 feet. Develop an expression for the acceleration of a fluid particle along the pipe center line. Plot the center line velocity and acceleration versus position along the pipe if the inlet center line velocity is 3 feet per second. A schematic diagram is shown of the horizontal pipe. The length is 6 feet. At one side 4 inch, at the other side 1 inch. Incoming flow, outgoing flow. X direction is taken in this side, this plane, y direction. So this is the given data, and what we need to find is written here. The basic equations that we know: del t of integration rho d v cut plus integration rho capital V vector dot d into capital A vector is equal to 0. V cut is taken for volume, capital V vector is taken for velocity. We know about the total acceleration equation. This particular equation we have come across earlier. This and this together make the convective acceleration, and the last term makes the local acceleration. We are assuming that it is incompressible flow and uniform flow. So the continuity reduces to summation of Cs capital V vector dot capital A vector is equal to 0. This is obtained on further simplification of the basic equation or the continuity equation. And also for the flow rate, capital Q is equal to capital V into capital A. It is equal to capital V into pi capital D square divided by 4. This is the area, this is the velocity. But capital D is equal to capital Di plus capital D naught minus capital Di divided by L into x, where capital Di and capital D naught are the inlet and exit diameters. exit diameter, inlet diameter, and x is the distance along the pipe of length capital L. X is distance along the pipe of length capital L. So this is the next step, which is generally required in some of the cases. Hence, capital VI is equal to pi into capital DI square divided by 4 is equal to capital V into pi into capital DI plus capital D naught minus capital DI by L into X. This whole is raised to the power 2 divided by 4. The velocity is same, so the equal sign is used. So this particular term is taken to this side. So we get V of X is equal to VI 1 plus capital D naught divided by capital DI minus 1 divided by capital L into X whole square. At 0 feet 3 feet per second, at 3 feet 7.68 feet per second, at 6 feet 48 feet per second. The acceleration, as we know, can be obtained by this equation. Convert acceleration, this, local acceleration, this. Similarly, for acceleration, we can obtain terms by differentiating capital V into del x of capital V. Ax is equal to Vi divided by 1 plus capital D naught by capital Di minus 1 divided by capital L into X whole square. Dot del x of capital Vi divided by 1 plus capital D naught by capital Di minus 1 divided by L into X whole square. On differentiating, we obtain this particular term. The basic differentiation rules are applied here, and on further simplification and further calculation, the simplified version or the equation for Ax as a function of distance x, capital X, this particular equation is obtained, which is 2 into V I square into capital D naught by capital Di minus 1 divided by L into X into capital D naught by capital Di minus 1 divided by capital L plus 1. This whole is raised to the power 5. Ax at 0 is equal to 2.25 feet per second square. Ax at L by 2 is equal to 22.6 feet per second square. And Ax at L is equal to 2.30 into 10 to the power 3 feet per second square. These values are the representative values which can be obtained on putting the values for x at the distances 0, 3 and 6 respectively. This is the theoretical graph, and this is the graph which is plotted between x-axis and y-axis. In x-axis, feet, which is the distance, and in y-axis, feet per second, which is the velocity, are plotted, and the graph comes out as like this. The values are plotted at 0, 3 and 6, and in between the values which are calculated can be plotted in the graph. This is the theoretical graph for the next segment of the graph, plotted between x-axis where the distance is taken in feet and in y-axis where the acceleration is taken in feet per second square. Graph plottings for 0, 3 and 6 are made. This is the first graph plotting and this is the second graph plotting. So with this I'd like to conclude my discussion regarding the solutions. Thank you very much.